Hi, in this video, we want to take a look at the properties of multivariate normal. Okay, so we're talking about the normal distribution. This is a very special case of various probability distributions. Now, why do we like normal so much? Well, first and foremost, because of the central limit theorem, a lot of statistics end up being approximately normally distributed. All right, so and the normal distribution comes up quite frequently in a lot of like naturally occurring situations. And even if it's not quite normal, a lot of times the bell curve, is a good approximation. Well, since we're interested ultimately in linear models for our purposes, it's very natural for us to look at multivariate normal since normal distribution is so important everywhere. And if you remember from like other linear algebra or linear models courses, like the undergrad versions, is that we need assumptions about we need to have certain things be normally distributed for us to be able to use different models, to use different statistics techniques. So first example is ANOVA, that we need to be dealing with normal distributed random variables if we're going to be able to trust the ANOVA p-values. And if I'm doing linear regression, I want to do hypothesis testing, I need to have the residuals be normally distributed. Okay, well, here we're going to kick it up a notch because in those cases, we're really talking about univariate. Here, we're going to be talking about multivariate. Okay, so first thing we want to take a look at is, let's say that y is a normal so it's a normal vector, length p. We're going to say that A is a constant vector. So lowercase a is a constant vector. Capital A is a constant matrix. A is k by p. K is less than p. Now, why do we have the k less than or equal to p aspect? The reason for that is because we want to have full rank. And this is very natural for the situations that we see ourselves in when we're dealing with data. So when we step out of theory and we start doing application, what this is saying is that we actually have more columns than we do have rows. So all right, so k is less than or equal to p means that we have fewer observations than we have variables. Okay, something to be mindful of. Now we're going to say that the rank of A is k. So it's a full rank matrix. All right, in this situation, if I take the dot product between the constant A vector and my normally distributed vector, then first and foremost, so pay attention to, is that dot products always give me a number. So it's going to be a scalar. So whatever I'm going to get is going to ultimately be univariate. Well, what is that univariate distribution? It's going to be normally distributed with the mean, really just replace the mean vector with the y, and that gives us the mean of this dot product. And then we're going to take A transpose, then our covariance matrix A, and that will give us our variance. All right, now something to pay attention to in this is that notice that A is going to be 1 by p. So 1 by p, p by p, p by 1. This is a 1 by 1 matrix. In other words, it's a scalar. So this is just one term. This is one number. This is one number. This is the mean, and this is the variance. Okay, so now let's look at another more complicated situation. This time, I'm multiplying the vector by a matrix. All right, so here we multiply A. Well, in this situation, really it is very similar to what we had previously, that the mean over, okay, so let me back up. This is going to be a length k vector. Okay, it's a length k vector from matrix multiplication, k by p, p by 1. So it's going to be a k by 1 matrix. So then it's going to be a length k vector. All right, well, what is the mean? Well, the mean is going to be just the matrix times the mean of y. That seems like that's how we would want it to be, right? And now, well, what is our covariance? Well, what I'm going to do, I'm going to multiply our covariance matrix by A on the left and the right, on the right by the transpose, and that will give us our covariance matrix. All right, now, how do we prove this? Okay, anytime that we want to prove the distribution of something, almost always we want to use moment generating functions. If I can do it with moment generating functions, that's probably the easiest way to do it. You can brute force this. And I thought about showing the brute force proof. I worked through it, but I realized it's just not worth it. Okay, so here's our game plan. What I want to do, I want to use moment generating functions. So I'm going to take what I have, the assumptions I've got going up here, everything before the then statement. I'm going to apply those to moment generating function that I have. Just start plugging stuff in, plugging and chugging, and then I'm going to take a look at what do I have after I take that expected value. And if I've done everything right, I'll have everything good. And then what I'm going to do, I'm going to take a look at the output. If I recognize the moment generating function that's the output, then I go, hey, that is so-and-so distribution, moment generating function. Boom, we've got it. Okay, so game plan. I'm going to say that Z is equal to A transpose times Y. All right, that's very natural for here. So Z is this random variable. We need to find the distribution of Z. So I'm going to take the moment generating function of Z. And now we're going to go ahead and make the assumption that if all the calculus works out as I work through, well, I'm going to make the assumption that I can do the calculus. And I'm going to pay attention and make sure as I go that there's no violations of the assumptions necessary for this to work out. Okay, so I go ahead and take the expected value of e to the tz. Okay. Well, when I get to here, what can I do? Well, really don't have much that I can do. So let's go ahead and let's replace Z with A transpose Y. Okay, let's do that. Okay. Now I've got that. Well, I'm feeling okay. Well, this is kind of like moment generating function. So I know it's always like a variable vector times my random variable, right? Okay, so to do that, what I'm going to do, you see how I have the parentheses here? Remember, matrix multiplication is associative. And here, this t is a scalar. So that's scalar multiplication. So because of the associative property of matrix multiplication, I can change the parentheses to be like this. Okay, well, that's interesting because now I have a vector times my random vector, right? Okay. If I write it like this. Okay, so now I look at this and I go, hey, that's exactly the format of a moment generating function on Y, but instead of t, I have t times A. Okay, so I'll go ahead, this is because of this format, this is the expected value of vector transpose times my random variable. I know, and t is a variable, I know that this is actually the variable of a moment generating function where this is the random variable. Okay, so what I've established is that the moment generating function of Z is a moment generating function of Y, but instead of t, it's t times A. Over here, t is one scalar. Here, t times A is a vector. So I'm going to need my multivariate version of moment generating functions. But that's okay because I've got a multivariate variable right there. Okay, so if we remember, if I think back, well, this is the moment generating function for Y regularly is just going to be this. Notice that it's e to the power of t transpose times mu plus t transpose sigma t all divided by 2. All right, over here is the mean, over here is sigma. Okay, so what I want to do, because I recognize this form, I can invoke this formula. When I invoke this formula, what ends up happening is I'm going to replace t with t times a. And I take this formula, I replace t with t times a, and I get this. Okay. Now I'm taking a look at that, and that's almost what I want, right? It's almost a moment generating function that's really juicy and nice. I realize that I can rewrite this as A transpose mu using the same associative properties, same properties we've used for matrix multiplication. And I can rewrite this as A transpose sigma A. Just I'm going through here and I'm just rewriting this. Okay, so now I go, hey, that looks really familiar. That looks like something from my, stat theory class. It looks like something from my actuary exam P, maybe. And I realized, hey, this is the moment generating function of a normal distribution where the mean is A transpose mu and the variance is A transpose sigma A. Well, if I recognize it as a moment generating function, I can automatically grab it. I know it's a normal distribution because there's a one-to-one relationship between the distributions and the moment generating functions. The moment generating functions in a lot of ways are similar conceptually to Fourier transforms, but Fourier transforms have different properties, like there are isometries and stuff like that. We don't have that nice property in moment generating functions, unfortunately, but they're still slick. They're the bee's knees, yo. All right, so now we're gonna do the same trick. I'm gonna take the moment generating function. I'm gonna manipulate it in some way until I recognize, hey, that's what I want it to be. And that's how the proof is gonna go. Okay, so we're gonna say that the vector z is A times y. Okay, A times y. And so then I'm gonna take the moment generating function of z. My goal is to manipulate this into a format that I recognize. And once I recognize it, I can just declare what the distribution is. Okay, so by the definition of moment generating functions, this is going to be the expected value of e to the t transpose c. Okay. Well, once I get here, I know what z is, right? Z is A times y. So I replace z with A times y. All right, I'm looking at that. And you know what? I'm going to go ahead and use that associative property of matrix multiplication once again because it's my best friend. And I put a parenthesis around it. So now I'm looking at it and I realize that this is the same as A transpose T and then transpose to the outside of the parenthesis. Okay. So then I realize, hey, once again, it's just like a moment generating function. I have a vector times a vector, and the second one's a random variable. I have a moment generating function because it's all in the exponent of E. So I know that this is the moment generating function of Y with the variable A transpose times T. Okay, now the moment I spot this, I can go and I can grab the moment generating function for multivariate normal, and then I just go ahead and throw it in there. So I take A transpose T. Oh, so the reason, and so realize that the mean in the moment generating function I'm going to grab, the mean comes from the mean of Y. The covariance comes from the covariance of Y, and that's where these two parts come from, this sigma vector, or sorry, the mu vector and the sigma matrix. All right, now my variable is here. What I'm doing, I'm just going and I'm plugging this into the formula. I'm replacing T, what would be just T, with A transpose T. Now I go through and I just do a little bit of matrix manipulation using associative properties and stuff like that. I can see that now I have this that's in the same format as multivariate normal moment generating function. Okay, so I can see that here I've got the T vector transpose times the mean vector. I have T and T on each side of my covariance matrix divided by 2. All right, from the formula, because there is a one-to-one relationship between distributions and moment generating functions when the MGF exists, I can go, hey, this is normal. Furthermore, the mean is A times mu because of this part, and the covariance is A sigma A transpose. Coming from here, boom, we've got it. So this is why we like moment generating functions so much. In your stat theory class, we kind of get told that moment generating functions are useful for computing moments. I don't really use it that way. I usually use it for proofs in other ways, but whatever, Okay, so here is a corollary. The corollary is something we get for free in mathematics because of the work we've already done. All right, if I have multivariate normal, we have a constant matrix and a constant vector. Then matrix times random variable plus the constant vector is going to be normally distributed with a proper number of dimensions. So here we're making the assumptions that the addition and multiplication is well defined. It's going to be A times the mean plus B. And then we have A times sigma times A transpose that is going to give us our covariance. All right, so remember, adding a constant does not change our variance of a variable, right? So similarly, adding a constant vector does not change the covariance of a random vector. Now, if I do multiply and then I add a constant, what does that do to the mean? It's like multiplying and then adding a constant, just like in the univariate case. All right, now the next one is, this one is an important one. And this is important for conceptually for like things like dimension reduction. This is important for, regression stuff that we do. This is important all over the place. All right, so if Y is multivariate normal, then for any R entries of Y, so here R is specified and that is the number of entries of Y we're interested in. What we're going to do, Y is a whole bunch of random variables. We're going to just cherry pick a few of them. We're going to cherry pick R of them. Then the vector of these R entries is multivariate normal with a corresponding mean and covariances. Okay, so how are we going to prove this? First thing we're going to do is we're going to go ahead and we're going to say, without a loss of generality, we're going to say that I can partition the vector so that we have the entries we're interested, then the entries we're not interested, or vice versa. I can't remember which way I went. But we're going to partition our matrix, or we're going to partition our vector, and we're going to move things around. Why can we do this? Well, there's a couple ways to justify it. I'm just going to say that if we permute things with an isometry, we don't really change things that much, and I'm just going to leave it at that. Why it's okay to do this. All right, so if I apply a permutation to our matrix, to Y and mu, and conjugate sigma with the appropriate permutation, then we can set it up so that the entries that we are interested in are together and the entries we are not are together on Y. So then what we can do, once we get to this version of Y, I can go ahead and just say that, the mean mu1 corresponds to Y1, mu2 mean corresponds to Y2, and then we're going to go ahead and make a block matrix for the covariance in a corresponding manner that matches the block matrix here. Okay, so let's say that Y1 is the R by 1 vector that we are interested in, and Y2 is everything we're not interested in. All right, well, if I just say expected value, it should be, rather clear that the expected value of Y1 is mu1, the expected value of Y2 is mu2. That's very natural. And we'll go ahead and say that the covariances, sub-matrices are exactly what we want. All right, so now so all I've done is, at this point, I've said, I'm allowed to change the order to make this easier on me. And once I have that, then I can use a representation that is easy for me to use in this proof. Okay, so now that we have things in an easy representation to work with, I'm going to choose some objects to work with that are going to carry us through on the proof. So what I'm going to do, I'm going to say that A is the matrix, identity matrix, and zero matrix. So here, I'm going to have the identity matrix, and then I'm going to have the zero matrix, and we're going to put them next to each other. All right, so I is the R by R identity matrix. 0 is the R by P minus R zero matrix. Okay, so remember, so what's going on here is A has as many columns as Y has entries, but it only has R rows. Now, if I think about this, the rank of A is equal to R, which is the length of Y1. Okay, that's not a coincidence, but I picked it that way for a reason. Okay, so if I think about A times Y, then what's going to happen? So if I take this matrix and I multiply by Y, then I've got Y1 on top of Y2, right? Well, by how I built this, all the Y1 entries are going to the identity. All the Y2 entries are going to the 0 matrix. Huh, okay. And this is full rank, right? So that means I can use the previous theorem. Okay, so by my selection here, A times Y is equal to Y1, right, which is the object that we're interested in. And it's full rank. R is less than P. Then I can go ahead and apply the theorem. So A times Y, it's going to be normally distributed with R random variables, with A times the mean, and then A times covariance A transpose. Okay, okay. Well, A times Y is Y1, right? So A times Y is Y1. Now I'm going to think about A times mu. Well, that's the identity matrix times mu1, mu2, right? So identity 0 times mu1, mu2. That's what I get right here. What's going to happen is that 0 matrix is going to cancel out, right? 0 is not going to do anything from the matrix multiplication. So the mu2 is going to be like, boom, gone, not even part of it. Now, I'm going to keep using the theorem because now what I'm going to do, I'm going to put A to the left of sigma and A transpose to the right. And so I have I times I next to 0. I have I over the 0 matrix. And now I'm going to do multiplication. Well, we have a formula for this type of matrix multiplication. And if I work this out, because the identities don't change the values, that's why they're called the identities, and the zeros are just going to be 0. So what would be coming from the 0 doesn't impact anything. So I can see really what's going on is that this part here just simplifies down to sigma 1, 1. Well, what is sigma 1, 1? That's the covariance of Y1, right? So I've got it. This is it. This is everything. Easy peasy lemon squeezy. Multiply these two together, I just get mu1. Multiply these three together, I just get sigma 1, 1. And that tells me that this is going to be exactly what I want for the proof. Okay, here's a corollary of this. If Y is a multivariate normal, then if I take just one individual entry, that's going to be normal, univariate normal. All right, well here, how do I get that? I just set R equal to 1 and I pick the entry I want. And boom, we've got it from the previous theorem. So the marginal distribution and multivariate normal are also normal. Okay, well, for multivariate normal, now here's something that is true. For multivariate normal, covariance equals 0 if and only if the two variables are independent. This is a big deal. Remember that covariance equals 0 does not imply independence in almost all situations. This is a special situation. If I'm dealing with normal and covariance equals 0, then I have independence. This is a big whoop-de-doo. All right, so for almost all multivariate distributions, so for every single multivariate distribution, independence implies covariance equals 0. But the converse is not true. Covariance equal to 0 does not imply independence unless we're dealing with a normal distribution and a few other special cases. All right, so let's go ahead and take a look at the next theorem. If I have V is Y over X and V is the appropriate normal distribution, then X and Y are independent if and only if the covariance matrix is the 0 matrix. Okay, so first and foremost, this is an if and only if statement. Independence implies covariance equals 0. I think we intuitively got that. I think we believe it. If you're sitting in this seat, You probably know it already. If you don't, well, you know now. Okay, so now we want to show independence. First thing we're going to do, we're going to assume that the covariance is equal to 0. So I need to use the fact that the covariance matrix is 0, and then I need to somehow manipulate things to get 0. Okay, well, if the covariance between x and y is 0, then the overall covariance matrix of B is the covariance of the y's, covariance of the x on the diagonal, and then 0. So we have this 2 by 2 block matrix. All right, so here is something that we need to remember. If we can factor the moment generating function, then we got it. Okay, so just remember, if I can factor the moment generating function, then we have the result that we want. Okay, so what I want to do, I want to take the moment generating function of V, and I want to factor into the moment generating function of X, the moment generation function of Y. All right, so remember that with exponentials take addition and they convert to multiplication, right? So that if I can take the exponent addition, convert that into multiplication, then I've got it, because if I can factor the MGF, we've got it. All right, so here we're only concerned with the exponent of the moment generating function. Why is that? Well, I mean, technically I could keep the whole thing on, but I'm not going to do that. I'm going to just go through and work through it. Okay, so I'm going to take the exponent of the MGF of V. All right, well, that's just this, right? I mean, just the normal MGF exponent. Well, now what I'm going to do, I'm going to rewrite T, mu, and sigma in a way that corresponds to how we broke up V. All right, go ahead and do that. So T1 transpose, T2 transpose, mu1, mu2, and we've got T1 transpose, T2 transpose. And well, here's my sigma, but notice I've got zeros because the covariance between X and Y are 0. And then T1, T2. Okay. All right, well, now let's go ahead and let's actually do the matrix multiplication. I'm going to multiply here. I'm going to multiply these 3 items. When I do this, you'll see that I have T1 and mu, T2 and mu. All right, nothing special so far. Now, when I do the multiplication here, notice that with these zeros, I'm not going to have, the multiplication is going to actually be relatively simple and light to do. And when I do them, if you go through and multiply it by hand, you'll see that we get T1 sigma YY, T1 divided by 2, and we have a similar thing for X. Okay, well, what I'm going to do, I'm just going to put all the 1 terms together, all the 2 terms together, and put them in a parenthesis. And I've got this. All right, so now I see that this is the moment generating function of Y1. This is the moment generating function of Y2. Right? I just see that I've got T times mean, and then T on each side of covariance, T times mean, T on each side of covariance, and oh yeah, I'm dividing by 2. I know immediately that this is the exponent of the MGF of Y1 and the MGF of Y2. Therefore, we know for certain, all right, so this exponent is equal to the sum of these 2, right? All right, well, if I think about what happens with E, and taking E to the power of something, and I've got addition, well, addition becomes multiplication, means I can factor the MGF into an X part and a Y part. I can factor the MGF into an X part and a Y part, means that I have independence between X and Y. Boom, we've got it. All right, a corollary of this is that if I have multivariate normal, then 2 variables are independent if and only if the covariance is equal to 0. All right, so why is this important? Well, normally covariance equal to 0 is not enough to say independence. But if I have covariance equal to 0 and I have multivariate normal, boom, we got it. It is independent. Now, if Y is normally distributed, I have constant matrices so that A times Y and B times Y have 0 covariance, then I know that A times Y and B times Y are independent random variables. All right, that's all I've got for you. Take care and goodbye.